this video, we'll compare the performance of linear logic and probit algorithms with the help of ROC curve. Recall our discussion about ROC curve in the lesson 1 video topic ROC curve characteristics, ROC curve. So first we'll create a performance object with prediction object, and we'll start with the linear algorithm. So linear model that we fitted values, and also we need to supply the training data up and down values. So this will create a prediction object, and from this prediction object we'll create our performance measurement object with the help of performance command PR, and we need as a measure we need true positive rate or sensitivity on as our y-axis, and we need on x-axis we need false positivity or 1 minus specificity as we have discussed in the ROC characteristic curve. So we'll run this command. So now I'll plot the ROC command. It is a very interesting measure to compare the performance or evaluate the performance. So I'll plot with the help of this plot PRF. So when I plot this, notice this is the plot. I'll again clarify it slightly smaller, so we need to have proper PRF plot. So this is our PRF plot. Now a good evaluation of this PRF plot can be done with the help of center line, which is 45-degree line, which gives 50-50 probability. So I'll use this 0, 1, which is basically 0 to 1 line. And remember this, if you recall, this ROC curve essentially measures different values, different coordinates of TPR, true positivity rate and false positivity rate, at different values of threshold, different threshold values. So it gives a complete view of the performance. So we have line type 2, and notice the line type. Now we can see that this model is somewhere between 50% line as we saw, and the complete 100% accuracy, it is somewhere in between. But in order to know the exact accuracy number, we need to compute the area under the curve. So for that, we'll use our performance object PR, and the measure is area under the curve. So we'll assign this AUC object. Now with the help of this AUC object, we can simply access the area under the curve with this command, and it is around 72%. So this is our area under the curve, which visualization we can also see the performance. Let us also calculate this for the logit object. We'll visualize also. So the same thing we'll do for our logit object. Let's do that. So for logit object, we get the plot looks like this. Again, very similar plot. In fact, it appears to be very similar to the linear object, but we can compute the numbers. Again, very same values we are getting, very similar values, which was expected because of their high correlation, almost 95 to 99 correlation. Let's do this for probit also now. So for probit, I'll do the same thing. So for probit object, let's plot. Again, almost identical graph we are getting. So if I compute the AOC, again the same, very similar values. Notice that we observed exactly identical values of area under the curve. So could it be the case that we have done some mistake in computing our fitted values? Are these some result of some computational error? Let's check the summary of these fitted values. So I'll compute the summary linear $. These are fitted values. So just compute the summary of linear model. Then we'll do for it logit also. Logit $fitted values, and we'll see the distribution. The numbers are very close. In fact, to the extent of 4 digit they are close, but they are not identical. As we can see, they are not identical. They are very close to each other. We can see for probit also. So you can see there they are not identical, but they are so close. They are so close in terms of their distribution, the minimum, first quantile, median and mean. And this was also borne out by the fact that the correlation between them is almost from 95% between linear and logit probit, and between logit probit almost 99.9%. So because of such closeness, such high correlation, the classification is also, the ones and zeros would be very similar, and that is the result that different thresholding values the area under the curve, the accuracy of performance is almost identical. So area under the curve, ROC curve is almost identical. For ROC curve, area under the curve is very identical. Quickly, to just summarize the video, we plotted ROC curve for all the three linear, logit and probit objects, and we noted that area under the curve for ROC curve is almost identical. This is ascribed to the fact that the correlation between all these, the fitted values of all three algorithms, that is linear algorithm and logit probit algorithms, the correlation is very high, and because of that, the area under the curve, the performance measure, is almost identical. In this video, we'll develop a simple machine learning system which will help the computer learn how to select the best classification algorithm across a class of algorithms. So we'll develop a simple machine learning system. Very often we would have heard of a cost function to be minimized in the context of machine learning algorithms. In this particular case, we'll talk about a simple performance function which we'll try to maximize. The idea here is to develop a performance function, a well-suited performance function to the algorithm, to these classification algorithms, and see which one of these algorithms help us maximize the performance function. So let's call this performance function as OPT for optimize, and let's define the parameters of this function. So in this function, we'll try to simulate some numbers. We'll use our fitted values, we'll use the actual values, and we'll use different threshold values. So we'll simulate different fitted values for a given threshold, compare them with the actual values, and try to create a performance object which will be maximized across different algorithms. So first, we need to use these fitted values. We need these fitted values. So for that, as we did earlier, we'll use the very simple if-else function. The idea is to, using these threshold values, create ones and zeros. So actual fit values are in the form of probabilities, if you remember. So we need to convert them into ones and zeros using our performance evaluation function. Once we have that, recall that we computed confusion or classification matrix object, and in that we will create that object again. It's a very simple object, so we'll just use this command cm equal to confusion matrix. In fact, we can simply copy paste this. Remember, we have already typed this, so we need not type this again. We can simply use this. We already have computed this. So I can type this command. So this command will help me extract all the three relevant objects, that is accuracy, specificity, and sensitivity. So we'll use this. Also, because we are using a number of 0 and 1 as for tau, the threshold, we need to tell that there are two possible levels to this variable. So two possible levels that are 0, 1. So because it may give us error, from my past experience I know that it will give error if we do not specify levels, because for 0 and 1 there is one extreme case where all the fitted values are either 0 or 1. So in that case we may get an error. To avoid such error, we simply define the levels in advance. Now with the help of the CM object, I can obtain all the three relevant measures, assuming that specificity, accuracy, and sensitivity are the relevant measures. We'll define our complex combined performance object, and this can be anything. You can give any weights or any complex function for your performance matrix of accuracy, specificity, and sensitivity. But to keep the elaboration simple, I simply use this simple average of all these three metrics. What are these three metrics? These three metrics are of overall performance are accuracy, sensitivity, and specificity. So I'll just use these three metrics. So it's one is accuracy, I'm simply using their averages just to demonstrate the point. You can imagine any complex performance function depending upon your taste, choice, and preference, but to keep the demonstration simple, I am using their simple averages, just the average of three measures, which is accuracy, sensitivity, and specificity. So I'm using the simple average to test my trained algorithms and tell my machine or the machine learning process that this function has the algorithm whichever maximizes this function need to be considered. So specificity. Now the idea is through this function I'll simulate a large number of threshold values. I'll simulate a large number of tau or threshold values, and then I'll generate number of performance measures for different algorithms, and then I'll see which one of these algorithms is able to maximize or provide the maximum level of performance across competing algorithms. To summarize this video, we created an optimization function where the arguments, that is fitted value, actual value and threshold values, will be passed, and this will give us our performance or objective function, which is simple average of accuracy, sensitivity and specificity. The idea is to simulate a set of threshold values and through which we'll generate a number of performance measurement values for different competing algorithms. In the next set of videos, we'll generate these performance values for our three competing, that is linear, logit and probit trained models. We'll generate these performance values and we'll see and compare and contrast which of these models are able to generate better performance. In the previous video, we defined our performance objective function. In this video, we'll simulate 1000 threshold values and then calculate the value of our performance objective function for each of the classification algorithms, that is linear, logit and probit models. So we'll compute the performance objective performance function. As a starting point, let's start with the linear performance object of the linear model. So how do we do it? First and foremost, we have a, remember the function, we have the fit object. We'll assign the linear $fitted values. So these are our fitted values. Then we also need to supply our actual values, which are trained $up down. So these are actual values. We'll start with the threshold value of 0. So that is our starting point. And we'll create a performance linear object. So this is our performance linear object where we'll assign the values. Here we are putting the values of tau. So tau we have as a sequence from 0 to 1. So our tau values are from 0 to 1 in a sequence. So minimum is 0, maximum is 1, and we need to give the length. So length is 1000. So 1000 is the length of our assigned values. In fact, we can remove tau equal to 0 from here. We already defined tau from 0 to 1. And then the performance object, we initiate the performance object with the value of 0. Later these values will be filled when the value is calculated, as we'll see shortly. So we have created a performance linear object. Now, in the next set of codes, we'll run a for loop, a very simple for loop, where we'll simulate the values, and for each value of threshold, we'll compute our performance object value. So notice a simple for loop, it starts from 0 to 1000. Now the code is very simple here. It's a very simple code. Just notice. So I have my performance object, performance underscore linear object, and in this performance, for each I, remember the I moves from 0 to 1000. In each I'll assign the value computed from my optimization function, where I supply in the optimization function. Here I'm supplying the fitted values, that are the fitted values by the linear object, then my actual values, and then here I provide this threshold, simulated threshold value. So notice this I moves from 0 to 1000 and it is divided by 1000. So I supply 1000 values, simulated values, which will be used to compute the value of performance object. Now I run these values. So we'll run our for loop here, and notice now that the loop has run, it will simulate a set of values. You can check also, you can run this. You can print these simulated values in the performance linear object. So we can check the head of our performance linear object. We can also check the tail of performance linear object, since they are varying from around 50% from smaller to larger values, but we'll compare with the actual thing. So this is how you compute the performance object for the linear algorithm. Similarly, very similar manner, we'll compute it for logit object, for the logit module. Now I'll not write the code again. I'll simply just change this small line of code here to ensure that these are my logit fitted values. And then here, instead of performance linear, I'll type performance logit. I'll run this function and just replace the performance logit here, and I'll run this loop. So this will assign in the performance logit function, it will assign the values. Similarly, I'll create a performance probit function where I'll assign the probit performance, probit model. So I'll use this probit model here. I'll change the names from probit here and probit here. So I'll just run these codes. Probit, I'll create a probit object. Here also, when I'm simulating the threshold values, I'll run the for loop with probit objects. To summarize this video, we created three performance objects. First is the linear, logit, and probit. Using our optimize function, which we created for measurement of our performance, we simulated 1000 values of threshold, and for different values for each object, we computed the performance objective function value and assigned them into our performance object of linear, logit, and probit. In the previous video, we computed the values of our performance object for all the three classification algorithms, that is linear, logistic, and probit, using our simulated threshold values. In this video, we'll try to compare the performance through visualization. So we'll compare the performance through visualization. As a starting point, let us plot the values of the performance object for logit object. So we'll plot the logit object. First, its tau values, threshold, then the values of the performance for different threshold values. We'll plot as a type line, color red, line width of 2 seems to be appropriate. We'll not name the y-axis, we'll keep the y-axis as empty. X-axis is common, so we can give a name of threshold, and the central heading is performance. So the central heading is performance. Let's plot this object. So we can see the object that is plotted. Now we'll superimpose other performance objects for the probit. Again, same, we can use the same commands. Only that we change the color to green to make a distinction. Other things remain same, line width and so on. Now we'll just copy paste this, and instead of probit, we'll use linear here. And the color will change to blue to make a distinction. Let's superimpose these. Now it would be nice if we can add a legend also, so we'll add a legend on the probably top left seems to be empty, so we'll use top left corner to add the legend. so that a user can see the distinction. Legend. So we have three items: logit, probit. Let's make it capital. Logit, probit, linear. Then we need to add the color also through fill feature. Red, logit is in red, probit is in green, and linear is in blue. So with this we add the legend finally. With this our plotting will be complete. Now notice the performance objects. Here for all the values, in fact for most of the values, the red one seems to be offering in terms of performance higher values. So the red one attains higher values for most of the threshold values, and the red one is logit. Next is the probit, which is green one, although they are very close, but still for most of the cases logit is higher. Linear is the lowest one. They are pretty close. As we said, this is expected because the distribution of ones and zeros is pretty symmetric, 50-50%, but nonetheless logit performs better. Then second number we have probit, and third we have linear. Lastly, if you want to extract a particular value, for example, you would mostly be interested in the maximum performance value and what threshold it is to train our algorithm. So we'll be extracting it very easily in our, notice the command. So I'm extracting that performance value, which is equal to max. So the maximum value we are extracting here, just taking the maximum value and we'll extract that. So along with its threshold as well. So the maximum performance is 0.672 performance object value at a threshold of 0.536. So so an algorithm which is trained through this manner would probably be better placed to have a threshold level of 0.536, and at that level the performance object will give a value of 0.672. To summarize this video, we computed various performance object values for different classification algorithms, that is linear, logit, and probit, for our 1000 simulated threshold values. We plotted all these performance values and superimposed for all the three classification algorithms, and we noted that for most of the values, logit algorithm performs the best, next probit, and finally the linear. Although the performances are close to each other, nonetheless for most of the threshold values, logit seems to be the best algorithm for classification. In this video, we'll start with out of sample fit performance evaluation. Recall that in the discussion around linear regression modeling on the video topic out of sample fit performance evaluation, we have already covered a certain number of measures such as error measures like RMSE, RSE, and so on. So we'll not repeat that discussion here. We can refer to that video. So as a first step, we will, using our trained algorithm on the linear object, linear performance object, will create the test object. First, remember, this was our linear object. It was simply computed as linear equal to lm up down variable, and it was modeled using sensex with the training data set. So this was our linear object, if you recall. So we run this command. This was our linear object. Now we'll use the same trained. So this is our trained object, linear, and we'll now work out with the test data set. The command is simple, predict. We'll use our linear object, but this time the data that we'll use, the new data, is test data. So this is our predicted object. The values are contained in predicted linear object. Next, we'll train our logit performance object. Logit performance object. Again, remember, we computed the logit object with the simple glm command, glm. We'll use the same formula for the linear one. So we'll extract the formula from there, and we use the train data set to train our algorithm, family of binomial models. under logit. So this was our logit model, train model using train data, and now we'll compute the test object using test data logit, and again we'll use the predict command. This is our trained object, which is logit, and we'll use the new data, which is test data. Again, the type is response. This is for logit probit type of variables. Sorry, the response type is equal to response for binary variables. So this is our predicted logit variable. Next, we'll generate our probit object, probit performance object. Again, similar command, probit. We'll first train our algorithm in the similar manner, GLM. So in fact, I'll just copy paste the previous commands and just make few spelling changes and save time. So I'll just copy paste it here. Notice is here now I'll change it to probit. The object will be changed to probit, and in the family I'll change it to probit here. So I'll run this command. Again, we'll change here the predicted object. The trained object is probit, so we'll change it to probit. Here also we'll change it to probit, and remaining things will remain same. So we'll project. This is our predicted probit object. As a summary aspect, we can check the summary of predicted objects. For example, we can check the summary of predict linear, or if you want, you can check the summary of predict probit and so on. Lastly, we'll just combine them, combine all the predicted objects. Let's call it table cbind data frame. We'll combine our predicted objects linear, predict logit, predict probit. So we'll combine them in the consolidated table, all the three objects that are there. In fact, you can check the correlation also if you want. You can just check the correlation across all the three objects. It's pretty high between probit and logit. We can see very high correlation. That means we can expect similar results and similar performance results with logit probit. The correlation with linears is less. Still, it is high at 91%, but still much less as compared to between logit and probit. In this video, we computed the predicted values for all the three classification algorithm using our trained object. So using the trained object, we predicted the values for all the three algorithms, and we noted that in the predicted values using out of sample test data, which is out of sample fit, the correlation between all the three algorithms predictions are pretty high. In fact, for logit and probit, it is close to 99%, while with linear object, it is 91 to 92%. This is ascribed to the fact that in our data, ones and zeros, that is positives and negatives, are pretty symmetric, that is 50-50%, both in test, train and original data set. Therefore, we expect the overall performance of logit and probit to be pretty similar, and that of linear also to be close to logit and probit models. In the previous video, we predicted the values using the trained model with the test data set. In this video, using these predicted values for all the three algorithms, we'll compute the ROC curve and compare and visualize performance. We'll also compute area under the curve to compare the performance of the three algorithms. Please note that a detailed discussion on ROC curves have already been done in lesson 1, video topic ROC curve. Also, a detailed R implementation of these ROC curves has been done with the trained data. So we'll not have a detailed discussion. We'll keep the discussion brief and we'll focus on the R implementation part. So we'll not have a detailed discussion. We'll keep the discussion brief and we'll focus on the R implementation part. So we'll first create a prediction object, as we have already done similarly with the training data set for the linear object, and we'll compare it with the test data, actual up down values. So this is our prediction object. Using this, we'll go to the performance, same as we did earlier, PR, and we use on x-axis we have true positivity rate, TPR, on y-axis, which is also our sensitivity, and on x-axis we'll have false positivity rate, which is our 1 minus specificity. So this is our performance object. We can plot this performance object very well. So we can plot it as we can see here. Along with that, we can also draw the 50% area line as we did earlier. So this is very simple using abline command 0, 1, line width of 2, maybe line type of 2. We can give it a color of maybe red, and this is the line. One can also compute area under the curve very simply. AUC equal to performance, and we'll supply our prediction object PR along with measure, which is area under the curve. So this will store in AUC. I can simply extract the area under the curve with this AUC y dot values, which is around 71.5%. Now I'll not write the code again. I'll simply copy paste these, and this was created for the linear object, linear performance object. Similarly, I'll create it for the logit performance object, logit performance object. Only I'll replace from linear, I'll replace it to logit, and I'll just compute the performance now. We have the plot here. This is the line. The values are expected to be pretty similar. Given the high correlation, we are expecting high values. Similarly, I can compute it for probit. As noted earlier, we may expect a very high similarity, predict probit. So this time we'll be using probit object, and I'll compute. So again, pretty similar value. This is ascribed to the fact that the prediction, the probabilities may be different, but ones and zeros will be almost identical. So we are expecting a very high similarity given the very high correlation in the fitted predicted objects. We saw the correlations were in fact more than 90%. So we are expecting very similar performance, as we can see here, around 71.5% area under the curve. So as per ROC, the performance is quite similar, but we'll create our more complex performance object to see how they are comparing with each other and contrasting with each other. To summarize in this video, first we computed the ROC, receiver operator characteristic curve, and then we also computed area under the curve. We find that given the high correlation across the fitted objects, the area under the curve and performance as per ROC characteristic curve is very similar. In the next video, we'll use these values, our trained algorithms, and then compute our objective performance function, for which we have already written the user defined function, and we'll say using the simulated threshold values, we'll compare the performance for all the three algorithms, linear, logit, and probit. Recall that we have already set up a performance object, which was simply the average of accuracy, sensitivity, and specificity. Now, using our predicted values for all the three algorithms, we'll compute various performance object values for 1000 threshold values that we'll simulate using the user defined function that we have already created. So we'll start with the performance object for linear model. This is quite simple. We have already seen that with the trained data, so we'll not repeat the discussion in great detail. We'll simply execute it. So this is our fitted values, predicted values using the test data and trained algorithm. These are our actual values, test dollar. These are actual values, and then our performance object, let's use this name performance linear. We'll keep the same name and we'll assign a table, which is nothing but a sort of data frame object. Tau will be a sequence. Remember, the taus here will be sequence of 0 to 1, and we'll keep the length 1000, same as earlier. Length is 1000. So 1000 threshold values will be created from 0 to 1 at equal intervals, and we'll initiate the performance object with the value of 0. So this initiation value is 0. So this will be our linear performance object. Now recall, we'll start with a for loop where I is the counter and 0 to 1000. So we'll start with 0 to 1000. So we include 0 and 1 so that 0 and 1 both are included in the threshold. And now performance underscore linear. In this, we'll assign the value of perform. We have initiated a value of 0 by default. So by default, there's a 0 value. Each time this for loop will run, one new performance value will be assigned. And this OPT user defined function we have already created. Linear dollar fitted values. In fact, I can simply use the fit we have already assigned to the predicted values into fit object. Actual values are also assigned here, and then I upon 1000. So this will be our performance object. I'll run this. So this performance linear object will carry my performance object values through simulated threshold values. In a similar manner, I need to create it for the logit object. So I'll just copy paste this code. I'll not change it much. So I'll use it performance object for the logit model. Only thing I need to do here is I simply need to just change this to logit, and rest of all it will also this one as well, logit. This one also needs to be changed. Other than that, okay, this one also needs to be changed. So now I'll run this entire segment. So this will also run. In the meanwhile, while the loop is running, I'll also create my probit object. So this is for probit. Again, I'll make the same changes. Probit here. Here the performance object is probit, and here also it is probit. So now I have computed the values of my performance object for the simulated threshold values for all the three classification algorithms. To summarize, in this video, we computed the value of our performance object using the predicted values for all the three algorithms with simulated 1000 threshold values. In the next video, using these performance object values, we'll compare the out of sample performance of all the three algorithms and also visualize the performance. In the previous video, we have simulated 1000 performance object values for our test data. In this video, we'll compare the performance of all the three classification algorithms using these simulated values. Since we have already done this exercise for training dataset, we'll keep the discussion brief and focus on the implementation. So we'll compare the out of sample performance. First, we'll plot in the similar manner. We'll plot the performance for the linear object, tau performance linear object for the performance. Again, same commands. We'll keep the type as L, line color as red, line width of 2 seems to be appropriate here. Ylab access y label will keep empty. Again, x lab will keep as threshold name, which is appropriate. And the central heading will keep as performance. So this will be with this we'll start plot, and we can see that the performance plot. Next, we'll add probit performance object. So just to maintain consistency, I'll use logit here. Next, we'll start with the probit object. Again, I'll use the same set of commands. Performance probit, performance. Other commands will keep same. Type L, column red, line width 2. We'll change the color to green. We'll maintain the consistency here. So for consistency, we'll run this as well. and next we'll post linear. So linear, and I need to change this to logit as well. Sorry. Here I'll take linear. I'll keep the color blue. So I'll again replot because there was some error, so I'll replot it. So these are the plots. Let me add the legends here as we did earlier. So we'll add the legend. Again, the top left seems to be empty, so I'll create the legend at top left. Names of legend, we'll give the names same as earlier: logit, probit, and linear. Color scheme remains the same, so we'll use that again. Fill, logit is with red, probit is with green, and linear is with blue. So this is my legend. So I'll run the legend command. The legend has appeared. Now notice, very identical to our train data set, in test data set also we note that the red one is the most outer one. That means the performance values, which is the average of accuracy, sensitivity, and specificity, is highest for most of the probability region, most of the threshold region. It remains higher for logit in red, probit in green, and linear in blue. So for logit it is highest. Probit is very close, but is still lower, but very close to it, which is expected because of the very high correlation in the fitted values. Linear is the lowest. Linear, the blue one, is the lowest, although relatively it's not that lower also, but still, if one has to choose, one will choose the logit and next probit. Lastly, if one wants to finally select the best trained model, one can simply, as we can see, the logit is the most optimum model here from our projected object. So, and if you want to select that particular observation and threshold value as well, as we did earlier, we'll simply choose this logit dollar performance and equal to maximum value. So we'll select the maximum value for our performance object, and this will help us extract the corresponding threshold value along with the performance object. So I'll just run this, and again we can see at tau of 0.569, which is the threshold value, we get a performance object value of 0.659. So this is the maximum performance value which we obtain for the logit object, and logit is supposed arguably the best classification algorithm at tau value of 0.569. To summarize, in this video we plotted our simulated performance object values. We observed that for most of the threshold region, logit model seems to perform best as compared to other two, probit and linear. It is closely followed by probit and then linear. We also extracted the best performance threshold value for logit object, which was around 0.569, and the performance object has a value of 0.659, which is simply the average of three accuracy, sensitivity, and specificity values for the model. To summarize this lesson, we modeled ABC stock price up-down measure, that is a dummy variable which is 1 for up and 0 for down movements, using linear logit probit classification algorithms. First, we trained the model using the training data set and examined various measures of model performance evaluation. These included parameters of accuracy, sensitivity, and specificity derived from confusion classification matrix. We also visually examined the model performance using ROC curve and computed the area under the curve. Next, we created a simple algorithmic system by simulating 1000 thresholding values and computed a comprehensive model performance object using parameters namely accuracy, sensitivity, and specificity with the test data to examine the out-of-sample prediction efficiency of the model. Overall, the logit model seems to have provided better fit and model efficiency, followed by probit and linear models. We also computed the marginal effects of the independent variables on the dependent variable for logit probit class of models and discussed the interpretation of the same.